So what have we done? We started with this range-min problem. We've seen applications. We've seen the sparse table solution, which was good, but not quite the best possible time. And now I've spent a lot of time talking about these ominous Cartesian trees, where it's not quite clear what they're good for. They can encode the information necessary for the problem with just 2n bits, but it seems they don't help us answer queries. So in this last part, we'll finally put all those pieces together. And we will use something that has become known as the 4 Russians lookup table trick, which it's named after four scientists, 4 researchers. I think all of them were at least from the USSR, but I'm not sure if they were all Russian. At least they were not in Russia at the time. They might have been born at least in Russia. The name is terrible. It screams ignorant American, but it got stuck. And to be fair, 4 names is a lot, so someone should eventually come up with a better name. But for the time being, this is it. And I'll stick to the predominantly used name. It's the 4 Russian table, and that's what we'll use. A second nice metaphorical term is bootstrapping, and this is the first step, and it goes hand in hand, usually with this 4 Russian trick. Okay, the solution that we've seen achieves this time, n log n pre-processing time, and constant time queries. That's the sparse tables, right? So just to be clear about this. So there's no magic going on in that part. Now a simple observation is, if our input was not of size n, but just ever so slightly smaller, just a logarithmic factor smaller, we can take m log m time, and it's still order n time, just because the divided by log n and times log m, that just cancels. So we don't have to work very hard, but if we could just break our input into blocks of logarithmic numbers each, dealing with those blocks would be possible using the existing data structure. And that's where the name bootstrapping comes from. You pull yourself out of the swamp using your own bootstraps. We will use the slow data structure that we've already had as part of the fast one by using it on a just slightly smaller input. Now, this weird definition, taking exactly log of base 2 divided by 4, why is that the right choice? You cannot make sense of that at this point, but it will be the final answer, and it is actually important that it's not just log n. We'll come back to that. So the first step, what we'll do is we break our array A into these blocks. So this is A. It starts with 0, 1, blah, 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 up to B minus 1. That will be the first block. And then it continues from B, B plus 1, up to 2B minus 1. Next block. 2B starts the next block, and so on. So that's easy enough. And B is just this magically chosen parameter. So far, so good. Suppose, let's make this a little bigger. So we have all these blocks. All of these blocks will have local to the block some minimum element. So note that I'm back to minima. I'm back to the world of range min, whereas the Cartesian tree section used maxes. But same thing, just to be consistent to the beginning, now switch back to minima. There will be one element within each block it could be the last one, or it could be at any position. But one element in each block will be the smallest one. Now I can take these and copy them out into a much smaller array. And that's what B does. So B is just take these 1, 3, 6. Who can't count to 6? So you just take those numbers and copy them into this array in the same order that they appear. So the ith block contributes the ith entry here. So that's the smallest elements in each block. And for this array B, we will build our sparse table data structure. So we can find range-min queries in B for any two indices in, well, the desired time, linear time pre-processing, constant time space. Now, well, this is an n to be distinguished from m. Of course, this only works because B is just much smaller than the original input n. So it's cheating in a sense, but it's fine. The problem with that is not every query can be answered with that. If I'm interested in a query that extends from here to there, it seems that this range-min query is not at all useful, because it's only about the blue elements, and there's the other elements here. In particular, the range-min in this range might have well been this red guy, this element here. Now, we know that this is even smaller than that one, but we don't know how those two, well, I mean, we know how they relate, but this might be much, much smaller than this one, so this might still be smaller than this. And we don't know about the others too. So the red part is not even a candidate in the blue list. There's no way that a range-min query on array B will return this red answer. So we can do something in the right amount of time, but we're not yet there. The next thing we'll have to do is to decompose a query. What is meant by that? For that, I think it's best to just copy the part that we already have, so I don't waste time on drawing this again. But let me take a slightly bigger query than the one I've drawn here. So I'll try to carefully erase that. Okay, almost. Just add the stuff I deleted. That's too big now. Okay, there we are. Suppose our query is a little bigger, and well, okay, I'll delete all the indices here because we know what those are like. Okay, suppose our query is a little bigger. It extends from here to here. The important part is any query can be written as something that spans, I should probably use blue, something that spans from one block border to another. I'll call that the inter-block query, because it is a query that talks about how blocks relate to each other, and it's aligned with block borders. That's the important part. It starts and ends at a block border. Now, this is not all. There's other parts of the query. they extend from here to here. Those are the intra-block queries. They lie totally inside a single block. And we have at most 2 of them. So any query, a general query, can be written as find the smallest, find the minimum of, well, one long interblock query and 2 small intra-block queries. Right? The range minimum of this red line, another way to say what I wrote here a little informally, is the range minimum of this entire range. It can either be one of these, or it can lie in the part that's outside the completely covered blocks. So the minimum can either be in the intra-block queries or in the inter-block queries, whatever element is the smallest overall. That's really all that I want to say about the query decomposition. And now you know that we can use this time for the blue part. That's what we already know. That was the easy part where we could just use bootstrapping. So what remains to do is the intra-block part. And for that, we need a smart idea. And we will use the fact that they lie inside this very, very small block. So it remains to solve the intra-block queries. Obviously, we have to do some pre-processing if the overall running time should be constant at query time. So we want overall the same running and pre-processing time. And that means I have to, so this means pre-processing for all n divided b rounded up, which is roughly n divided log n blocks. That's quite a bit, and we have to be careful how to do that. One way to do this is the observation of the 4 Russians. So we have many blocks. But they're all short. They all just have b numbers. And we only need the local arrangement queries inside the block. And we know what that number was. I omit the floors and ceilings in the following. Maybe also here I should just make them gray. And now we'll use our Cartesian tree insights. The Cartesian trees of B elements, so the Cartesian tree for one block, they can be encoded using 2B bits. And that's still a fairly small number. That's log n divided by 2. Now, why is that interesting? That means there's not so many different Cartesian trees. That means the number of different Cartesian trees is at most 2 to the 2b, 2 times 2b, sorry. There's 1, 2 from the bound on the Cartesian trees, just to go back briefly and convince you that this was the case. There's 1, 2 from here. And there's a second 2 from using... Oh, that's not true. I'm sorry. I confused myself. That's just 1, 2. It's the same 2. Okay, sorry about that. The number of different Cartesian trees is 2 to the number of bits. That's the number of different bit strings of that length that we have. And now let's compute this number. 2b is a half log n. So you can write this as first take to the log n and then take that to the power 1/2. And that's nothing but square root of n. So there's only square root of n different Cartesian trees, but we have almost a linear number of them. Well, by pigeonhole principle, we have many equal or many equivalent blocks. Equivalent with respect to range minimum queries. And that's all we care about for this data structure. And that brings us finally to the 4 Russians lookup table. So that means we store 2 things. For each block, we compute and store its type. And that is the parenthesis string of the Cartesian tree. And we replace this by zeros and ones, so that is a number. So I can write this, that represents a number in binary. And that number is in the range 0 up to square root n. Because there's only so many different Cartesian trees. Okay. And the second thing is compute a big lookup table of all RMQ answers for all possible types. So what this will look like is there's a block ID. That's this thing. And then we will have an index I and an index j. And the last column that tells us the index of the range mean in that range. And that will be filled during the pre-processing by just going through all possible block IDs, decoding it as a tree, filling in that block ID. So there will be the block IDs all zeros. Well, that won't be a valid tree, but we don't really care. We fill those with some garbage entries. So there will be, maybe let's do a real tree. And it'll be clear that there's parts of the table missing. So there's something, and then comes some tree. Say it's a fairly small one. Okay, we can practice the decoding of the tree. So that is this tree. Now I and j can be numbers between 1 and 4. So we'll just have all possible combinations. And in that tree, so it'll be 1, 2, 3, 4. Comparing 1 and 2, 2 is higher up in the tree, so it's the lowest common ancestor, so we'll store 2. Then we'll have the same tree, and we'll have 1, 3. In that case, 3 is the answer. And we'll have another copy of this with 1 and 4. In that case, also 3 is the answer. And we will have 2 and 3 and 2 and 4. And so it's always 3. And that's probably all combinations. And we do this for every possible block ID and every possible combination of I and j. That sounds like an excessive computation at pre-processing time. But we only have square root block IDs. I and j are each just from the range of b. So we just have rows. We just have square root n times b squared rows. And that's not that big a number. It's essentially square root n times log squared. Oh, come on. So this is much smaller than n, and we can fill all those entries in linear time, no problem. It's actually a fairly small cost. For each block, computing its type might be the more dominating part of the running time. But we can also compute these bounds parenthesis strings in a linear scan. That part I will not go into detail, but this is also possible with a fairly simple algorithm. So also this part can be done in linear time. So in total, the pre-processing consists of the following steps. we find the block type. We compute the lookup table. And we compute the bootstrap data structure for the block minima, which we also have to find. And all of these take linear time in the input size. And that way we get the overall time for the pre-processing to linear. And the query time is still constant because for a query, we have to break the query up into these three parts. The intra-block query, we use the bootstrap data structure, the sparse table data structure. And for the intra queries, we use just the table lookup in the big for Russians table. So we look up the block ID. We know what the indices are. So we look up RMQ in the big table by using the lookup ID as the first index, then I, and then J. So that all takes constant time. Each of these two takes constant time. That gives us 3 values. And so what remains is to find the minimum of these 3 values. That can also be done in constant time. And that's the final result of this section, this unit. It's a linear preprocessing constant query time solution for the range minimum query problem. It took us a while to go through the details of first how to find the Cartesian trees. And this was important because it allowed us to bound the total number of different blocks that are equivalent with respect to range minimum queries, which then allowed us to do this table lookup trick. So again, the table lookup trick really is to exploit that we have many of these blocks, but only few different types, only few ones that are really give different answers for the queries we look at, range min in this case. And the technique is more general than that. So we rather fill this lookup table for all the different nodes instead of pre-computing the answers for every single block, where many of them would have the same answers anyways. And as mentioned before, a consequence of this is that we also find this linear time pre-processing constant query time longest common extension data structure for strings, together with suffix array construction in linear time and LCP construction in linear time. This finally gives you a practical and useful implementation of all those string algorithms that we discussed. And I think that's a nice climax and nice finishing point for this module. We started with small little steps, but then by combining, each of the little steps wasn't too tough with a few exceptions, but by combining them all together, we can build very sophisticated algorithms and data structures for strings. And by keeping a little bit an eye on what we use, these remain practical and remain useful in all kinds of applications. So I want to stress that the solution we found is a bit complicated, but it gives us the optimal preprocessing and query time, because if we want constant time at query, we have to do the preprocessing, and preprocessing has to read the input at least once, and that already gives you these orders of growth. It's also a topic that that's dear to my heart because I worked on it for quite a while. And while the solution I presented to you now is not a very recent result, it's not from me also, but looking at how to reduce the space usage of these data structures is something I worked on. I said at the beginning of this unit that essentially the space is bounded by the pre-processing time, and that's true. But it turns out that the space here is in words and not in bits, and you can bring the space down further. And a second interesting step is we can avoid to actually access the array at query time, which our solution currently still does if you look at how we answered queries. To find which of the minima of the three parts that we partitioned the query into, we still need to the array to find out which of the partial solutions is the overall solution. And it's possible to find data structures that don't need that. So you change the game that the array is given to you at the beginning, then you can look at it and take notes, construct your data structure, but then I'll take the array away from you. And you can still answer range-min queries in the way we defined them, but you don't need access to that data, which apart from being a fundamental question, how to do that might also be cute from a, I don't know, data protection point of view. You can give this data structure away to another person, but you can prove that they will never get access to the actual values in the array. They can only ever answer range-min queries. With that, I'd like to close the Unit 9, and I'd also like to close Applied Algorithmics. I really enjoyed this module and doing that with you.